Leaving Cert Higher Level, Paper 1, Question 4 in 2015 started with a complex number fraction question. 2 over Z1 is equal to 1 over Z2 plus 1 over Z3, and you're given Z2 and Z3. So if we write that out, 2 over Z1 is equal to 1 over Z2, which is 2 plus 3i, plus 1 over Z3, which is 3 minus 2i. And if we simplify the right hand side, we're going to get 1 by 3 minus 2i. So we're just going to get these two denominators on top. 3 minus 2i plus 2 plus 3i over the denominators multiplied. 2 plus 3i by 3 minus 2i. If we simplify this down, we're going to get 3 plus 2 is 5. 3i minus 2i is plus I. Over, and we multiply the bottom out, we're going to get 3 by 2 is 6, minus 4i, plus 9i, minus 6i squared, which we know is going to become plus 6. So we're going to get 5 plus I, over 6 plus 6 is 12, and 9i minus 4i is plus 5i. Now, when we have a complex fraction, we have to multiply by the conjugate of the bottom to get rid of the I on the bottom. So let's multiply by 12 minus 5i over 12 minus 5i. And that's going to give us on top 60 minus 25i plus 12i minus 5i squared. And on the bottom, it's just going to, it's like the difference of two squares. We're going to get 144 minus 25i squared. The middle terms cancel, and that's why we have multiplied by the conjugate. So on top, this is a plus 5, so we're going to get 65 minus 13i over 144, and this is plus 25, so that's 169, and that's equal to 2 over Z1. So we can invert both now. So we can divide the right hand side every term by 13, so 2 over Z1 is equal to 5 minus I over 13. And at this point, we could let Z1 equal A plus BI. So we're going to have 2 over A plus BI is equal to 5 minus I over 13. Cross multiplying here, we get 2 by 13, 26, equals A plus BI times 5 minus I. Now, if we multiply out the right hand side and equate the real parts and the imaginary parts, we'll have two equations in A and B. So I'm going to put a 0y here. And then the right hand side becomes 5a minus ai plus 5bi minus bi squared. So that's the real parts are 5a, and this is going to become plus b. That would have to be equal to my 26. And the imaginary parts are, if I take a plus I, I'm going to have 5b minus a. Just take that 5bi minus ai. So if I equate my real parts, 5a plus b is equal to 26. And 5b minus a is equal to 0. Now I need simultaneous equations here. So if I multiply this one by 5, I'm going to get 25b minus 5a is equal to 0. Bringing that across, minus 5a plus 25b is equal to 0. So I'm going to get 26b is equal to 26. B is equal to 1. And if b is equal to 1, using this equation, 5 by 1 minus a equals 0. A will be equal to 5. So I'm going to get 5 plus I is equal to Z2. Part B of this question, let W be a complex number such that W to the power of n is equal to 1 and W is not equal to 1. And S is equal to 1 plus W squared plus all the way to W to the power of n minus 1. Use the formula for the sum of a finite geometric series to write the value of S in its simplest form. Okay, a kind of strange question this, but the math involved is actually really simple. A finite geometric series, the sum of n terms, is equal to a times 1 minus r to the power of n over 1 minus r. So we just need two values. We need a, which is 1, and r. What do I multiply 1 by to get w, and w by to get w squared? R is equal to w. So s then, the sum of all of these, which is equal to a, which is 1, by 1 minus r, which is w to the power of n, over 1 minus w. And we're told here this w to the power of n is equal to 1. So this works out to be 1 times 1 minus 1, which is 0. So we're just going to end up with a 0 here. So it's equal to 1 times 0 over 1 minus w, which is equal to 0. Strange question.